Hi, this is Luke Jane from Vertex Tutors, and today I'll be tackling the second question of 2015's AP Calculus BC FRQ. Last time we looked at question number 1, so continuing onwards, we are now met with a velocity question, which you end up seeing pretty frequently in these. So I'll read it out. At time t is greater than 0, a particle moving along a curve in the xy plane has position x of t and y of t with velocity vector v of t equals cosine t squared e to the 0.5t, and at t equals 1 the particle is at the point 3, 5. So a lot to digest here. I think one thing to take note of is that position and velocity are related through derivatives, velocity being the derivative of position. And then if you take the derivative of velocity, you get acceleration, but we won't really need that for that question. So I have worked through the sphere response and have made sure my answers are correct. So I'll basically be walking you through the process that I went through. First question, part A, asks us to find the x-coordinate of the position of the particle at t equals 2. So again, just a refresher, we can see that we have position and velocity, and we're trying to find the x position of the particle at the t equals 2, so s of 2. Again, one thing that you need to remember about integrals is that when you have a constant, so like if s of t has a constant in it, when you end up taking that derivative, the constant gets removed. That's why when we take an integral, you have to add the plus c back in order to make up for it. So I just put an example here of that. But in our velocity examples, we are given the velocity equations. So in order to account for these being derivatives of the position, thereby meaning we have to integrate to get back to the position, we have to add a constant. And that's why we were given this initial condition. We know where the particle is at t equals 1. We know that its x position is 3. So we can add that into an equation, saying s of 2 equals 3 plus the integral from 1 to 2 of v of t dt. So this is basically telling you where does the particle go from 1 to 2. And you can see it actually comes back a little bit towards the origin as it ends up decreasing, and we are left with an x value of 2.557. Again, in these FRQ problems, you want to round to the third decimal place, and you find this just by using the cosine t squared equation and plugging in on your calculator. The first two questions of the FRQ will be calculator, and the final four will not be. On to part B, from 0 to 1, there is a point on the curve at which the tangent line to the curve has a slope of 2. At what time is the object at that point? So here's something that might slip you up, is that you might start trying to use these equations immediately that are used for velocity and trying to find this. Well, actually, this curve that is referring to is this curve, which is the xy plane that has position x of t, y of t. So we aren't actually given those functions. However, we know that the derivative of a function, such as velocity when compared to position, is the slope of the tangent line. So we're basically asked, where is the tangent line a slope of 2? Where is the velocity a slope of 2? So with that understanding, we know that basically we want to see where the v of ty over the v of tx, right, delta y over delta x, is equal to 2. So we can just plug in our values, and this is, lucky for us, just another plug and chug calculator problem where you're able to set up an equation like this. You can use graphing, you can use all sorts of different methods on your calculator itself to ultimately find t equals 0.840 in this instance. On to part 3, or part C I should say, where we want to find the time at which the speed of the particle is 3. Now, here's something important about velocity and speed, is that both of these have vectors components, meaning that if you have something like this, right, you have some velocity in the x direction, some in the y direction, you end up having your net velocity. So when asked for a speed of 3, it's basically asking you where this final velocity, right, this sum that goes in a diagonal direction equals 3. Now, one relationship that I do want to talk about is basically speed is just the absolute value of velocity. So in velocity, you're allowed to have negative values, like you can be going negative 50 miles per hour. With speed, there's only 50 miles per hour and no negative signs. So even though I wrote velocity here, just know that speed is basically the same thing with an absolute value sign. And as my work sort of spoils for you, we're going to be using the Pythagorean theorem because we have some x value, we have some y value, and we're trying to find the completion of a right triangle. So we get x squared plus y squared, which would normally, if we write it the Pythagorean way, would be a squared plus b squared. So if we just set up an equation, 3 equal to the cosine t squared, sorry, this should say squared as well, and plus e to the 0.5t also squared, we get to use our calculator one more time, and we get that t equals 2.196. And again, I listed here that speed is the absolute value of velocity. So if you, in case somehow you end up getting like when you square both sides that this is a negative 9, that is still totally fine. You just need to make sure your answer accounts for it. So once we finally look at the last part of this question, part D, we just need to find out the total distance traveled from the particle from t0 to t1, which is actually surprisingly simple because, as I mentioned before, the integral of your velocity will be your position. So we need to use, though, our net velocity, our net speed, because we aren't just seeing how far it traveled in the x or how far it traveled in the y, we're trying to see how far it traveled in total. So this is just the simplified version of the equation we had up here, and when we integrate from 0 to 1, we get 1.595. So overall, this question, just using your understanding of how position can be derived into velocity, how velocity can be integrated back into position, and basically just using equations in your calculator to get all the answers that you needed. All right, I hope that helped, and I'm happy that Vertex Tutors is able to provide another FRQ video.